Okay, so we did some problems about springs. And you might have wondered why we were talking about springs in the middle of a unit about work and energy. And the reason is that after gravity, which is a constant force, the next easiest force is a linear force, and that's what springs do, at least perfect physics springs. So if you have a spring that's relaxed with some mass m on it, and it's stretched out some distance x, some displacement from equilibrium, then we say that the force is equal to minus k times x, where x is the displacement from equilibrium and k is called the spring constant. It's simply the ratio of force to displacement. The minus sign here indicates that this is a restoring force, which means that if you displace the object in one direction, the spring brings it back. So the force acts opposite direction to displacement. Okay, so let's then try what we have for calculating the work. So we said that the work that's done by a force is from, say, initial to final, that force times some path summed over that whole path. And so for our spring, we have the sum of minus kx dx from, let's say we go from the initial is at rest, and then the final is it's stretched out, like this. And we're going to find the work done by the spring. Okay, so let's see. So the final was x. So this is going to be minus 1/2 k x squared from 0 to x. So the work that's done by the spring in this case is minus 1/2 kx squared. Now, you might be worried that the work that's done by the spring is negative, but that's okay. The spring is slowing down as it travels from x equals 0 to x equals some positive displacement. So if something's slowing down, it's losing kinetic energy. So we can say that the change in the kinetic energy is therefore this work. Remember too, though, that we said any time that we find a work is equal to some function, initial and final, then we can define a potential energy as negative to that function. So for this case, that means that the potential energy is 1/2 kx squared. So now we can use conservation of energy. So let's do a simple case where we have a slope and we have a cart that's coming down the slope, and it starts from rest and it ends up compressing a spring. And we can figure out how much that spring has to be compressed. So for example, if you start at the top and you're at some height, say h, above the spring, and then you start with a k plus u. Initial is k plus u final. So initially we have no kinetic energy, plus we have an arrangement energy of mgh due to gravity, and afterwards we have some 1/2 mv squared plus now nothing due to the gravity. Okay, or if we want to find the final position being when the spring is compressed and it's at rest, that means then instead of being in the valley like this, if we have the spring compressed and the cart at rest with respect to the spring, then we get 0 plus 1/2 kx squared. So you can solve this problem if you're given, say, some h, you can find some x. Or if you're given some v, you can find some x. All you have to do now is solve.